guys, welcome to All Electronics. I'm Gregory, and in this video we are going to see on the bench and understand how a parametric oscillator frequency divider works. We're gonna take a look on the circuit working on the bench, and we're gonna go to the whiteboard to understand its behavior. Take your coffee and come with me. Well guys, we are exciting the parametric oscillator with 2.6 GHz using this frequency synthesizer here. Here we have the circuit prototype based on an oscillator I already shown here on the channel. You can see it clicking here on the balloon. One of the connectors is the input at 2.6 GHz and the other connector is the output at half the frequency, 1.3 GHz. We are using the parametric behavior of the oscillator as a frequency divider. Here we see the output frequency exactly 1.3, half the input frequency, and here on the spectrum analyzer we see the very clean output tone. Don't care about these bottom fluctuations here because they come from my LED lights here on the lab. The full setup of the experiment is the signal synthesizer exciting the parametric behavior of the oscillator, two power supplies, one power supply powering the circuit and the other used to bias the varactors of the oscillator, and I'm using a power splitter, a homemade power splitter, to split the signal between the spectrum analyzer and the frequency counter. So, what is parametric modulation? And of course, how can you use it to make an oscillator works as a frequency divider? Let's see. We create the parametric behavior when we modulate a parameter of the system. In the case of this circuit here, we are changing the capacitance, we are modulating the capacitances of the oscillator LC tank. We are changing in real time a parameter of the circuit. This is called parametric modulation, and parametric modulation can lead to parametric oscillation, or in this case injection locking, by subproducts in frequency generated by the parametric modulation. Let's understand it better. Let's start with a simple example. If we have a parallel tank, resonator tank LC, with an inductor and a capacitor, we know that the frequency of resonance will be F equals 1 over 2 pi square root of LC. This is the common formula we use to calculate resonance of a very simple LC tank. But now let's imagine we are changing a parameter of the circuit. We are changing the capacitance. So we are modulating the capacitance inside the function that defines the frequency of oscillation. Now we have an input signal that is applying a sinusoidal signal that changes the capacitance of the capacitor. We are modulating a parameter of the function that defines the frequency. Now the instantaneous frequency of oscillation, this doesn't exist, is only an example. This formula here does not have any physical sense. The truly mathematical behavior of this is much more complex. But here we can see that now the instantaneous frequency is a function of time because the capacitance is a function of time. We at least can see that the behavior of this circuit needs to be much more complex than a simple LC tank. And it is. First, let's attack the problem from the perspective of energy. After we understand the behavior from the perspective of energy, we can go to the perspective of signal to understand from an RF perspective how the frequency divider works. Let's imagine that we already have some energy inside the tank. We know that energy on an LC tank will be represented by voltage in the capacitor and current in the inductor, and the energy will be transferred between the capacitor and the inductor at the resonance frequency. So let's imagine we already have some energy on the tank, and the representation of the energy when measured as a voltage parallel to the tank will be oscillating at the resonance frequency. Okay, this is the voltage parallel to the tank. Of course, in the real world we know that the energy would be getting smaller because it would be dissipated by the real losses of the circuit, but here we don't have losses and we have energy being represented as voltage, and when the voltage is zero is because the energy is all represented as current. So in this point we have the maximum current. Here we have the minimum current, the zero current condition, where we have the maximum voltage. Energy is going to the capacitor, inductor, capacitor, inductor. Okay, now guys, let's imagine that we're gonna apply an input signal that modulates the capacitance. Modulation of the capacitance is exactly equal to applying an external force mechanical force pulling and pushing the two plates of the capacitor. We are changing the capacitance. A signal that modulates the capacitance could be actually a mechanical force changing the distance of the plates of the capacitor. Remember, we are trying to understand it from the perspective of energy. The input signal, the input force you're gonna apply on the capacitor will be at twice the frequency of oscillation of the tank. Twice the frequency, okay? When the voltage in the tank is increasing, we're gonna pull apart the plates of the capacitor. We're gonna apply a force in this direction. Distance of the plates will increase, and as the charge is constant, we know that charge is capacitance times voltage. As the charge is constant, the capacitance is decreasing, voltage will increase. Pulling the plates of the capacitor, we are helping the oscillation. We are increasing the voltage. Voltage is trying to increase, and we are actually increasing the voltage, pulling the plates of the capacitor. And in this way, we are adding energy. The mechanical force we are using to pull the plates is adding energy to the circuit. Remember, energy is proportional to voltage squared. So if we generate an increasing voltage synchronized with the oscillation, we are adding energy to the circuit. We injected energy on the system, pulling the plates of the capacitor when the voltage was going up. And now we need to return the capacitor to the original position when the voltage slope starts to go down. This is why the parametric modification of the circuit needs to be at double the frequency. We returned the capacitor to the original position, so we didn't remove any energy of the system, and now when the voltage flips, it needs to increase in the opposite direction. So we need to pull again the plates of the capacitor. Pulling the plates at the moment the voltage reverses, we add energy again on the system. So modifying the capacitor, we injected energy on the system, and actually this voltage here would be increasing, because we are adding energy to the circuit. This voltage here would actually increase. This is parametric oscillation. We changed a parameter of the circuit or the system at double the frequency, and we induced an oscillation at the resonance frequency of the system. This is parametric oscillation. Changing the bias voltage of the oscillator varactors, we can clearly see the behavior of injection locking by parametric modulation. Here we are injection locked, and we can go out of injection, changing the bias. Here we are getting far from injection, and here we see only parametric modulation without injection. We are entering injection locking. Now we are injection locked. And we can see that around the injection point we have tracking of the input frequency. So for small fluctuations of input frequency, the parametric modulation keeps the output frequency locked. Let's change the input frequency by 1 meg, and we see the output frequency changing by half 1 meg, 500 kilohertz. 1 meg change on the input frequency, we have exactly half megahertz change in the output. From the RF perspective, from the signal perspective, as an electrical engineer, I think it's easy to understand and is more helpful to understand the signal using the idea of parametric modulation. What is the idea of parametric modulation? We are changing a parameter of the system. Here we are changing the capacitance, and of course you already spotted that modulation of a parameter, if we are changing a parameter in real time, we are generating non-linear behavior. So this filter here is actually, from the signal perspective, a filter and a mixer, because we are generating different frequencies at the output than we have at the input. We have harmonic mixing here. And this is the fundamental idea of the usage of parametric oscillation and parametric modulation to generate injection locking in the oscillator, so it behaves as a frequency divider, and in this case a microwave frequency divider. We can see that this condition here is true if we have V in at the input. At the output we're gonna have V in over 2, half the frequency. Here in here is frequency. Sorry guys, it's not voltage. Frequency in, we can see that this condition is true because if we have F over 2 entering a nonlinear circuit that generates frequency mixing, harmonic mixing with F in, we have the condition that in the output here, we're gonna have F in over 2 also. So we have positive feedback over the amplifier and we have oscillation at half the input frequency. We can see that from the signal perspective, if we change the tank with a mixer, F out will have a component at FA minus FB. And of course, guys, F in over 2 equals F in minus F in over 2. The two inputs. Of course, this condition will generate positive feedback over the loop. This is the signal perspective, but actually we are generating injection locking of the oscillator because we are converting the energy of the input signal. We are taking energy from the input signal and down converting the energy to half the input frequency, generating injection locking of the oscillator. So guys, I hope you enjoyed this video. If so, please subscribe to the channel, give it a thumbs up, share with your friends, and I see you in the next video of All Electronics.